Hi, uh, right now I want to present about Cfir, fast and effective long text to image retrieval for large corpora. My name is Victor Poli and my student ID is D1229004. This is for data engineering class. Okay, so this is my outline. There are introduction related works. For related works, there are small-scale and caption-based text to image retrieval, large-scale text-to-image retrieval datasets, and challenges in MLLM-based approaches. For methodology, there are proposed decoupling Bayes tree, entity-based ranking or ER, summary-based re-ranking or SR, and the others is experiment, analysis, and conclusion. So, text to image. As we can imagine that if we have a question, then we need to ask. After we ask, then it will go to smart search in our phone or in our computer or laptop, and it will go for uh, it will smart lookup or it will search for it, and after it uh, search the specific words or something, then it will find the relevant documents. And after that, the question plus relevant documents go to the MLLM. And after that, it will generate the answer. The generated answer is based on provided documents. And from this, it will go to us again in response. So here we can see that this is example of the lengthy document query from atomic. There are so many words, and the others is the short caption of query from MS Coco. So from these words, we see here in the second example, a short caption query from MS Coco. The caption is young basketball players run down the court in game of basketball. And the second caption is the young boys are playing a game basketball. So the exact matching image start from these words, it will show it in here as the image. So from these words, we can have an image of someone playing basketball. So this figure one as a comparison of example from Atomic and MS Coco dataset. So for the Atomic, it will take more words to have this multifaceted corresponding matching images. So in the second figure is the left is up. This left is plot of the average text token between MS Coco short sentences and atomic long documents and their summaries, and in the right is the number of training and testing images of MS Coco and atomic. So MLLM limitation has a limitation. So we can say that MLM-based methods face limitation, particularly in the context of real-world use cases that involve large-scale, diverse, and ambiguous data, such as that illustrated in Figure 1 and Figure 2. First, MLMS-based methods often ignore efficiency concerns. Their model-based similarity in inference methods are computationally demanding, requiring encoding between each query, vector, and image embedding when ranking. This can result in a computation time of up to 22 hours for a single inference for a large test set, limiting their utility in large-scale retrieval application despite their high accuracy. And second, real-world use cases often involve complex queries and images with multiple objects. This contrasts sharply with the comprehensive but short caption found in datasets such as MS Coco and Flickr 20K, 30K, sorry. The nature of this complexity undermines the effectiveness of injective embeddings, which attempt to map diverse meanings sensed to a single point in shared space, which could be inaccurate, weighted geometric mean of all desirable points. This is particularly problematic in long text query to image retrieval tasks, where accumulated ambiguities significantly hinder the performance of multimodal large language models. Third, injective embedding struggles with partial text to image association. In a long query, only a subset of sentences may relate to specific regions or aspects of an image, while the rest discuss unrelated subjects. Additionally, a single sentence may describe just a particular region of an image rather than its entirety. So this is the uh, ER classifier for or uh, entity-based ranking. To address these challenges, this paper presents a novel two-stage coerced, coerced to find index shared retrieval or Cfir framework. So the first stage is entity-based ranking or ER, and the ER result is used to construct a shared entity-based image candidates index. ER is designed to be computationally cheap using pre-computed image embedding from a cache by replacing the entire document with a representation comprising its entity as the query. We transform the retrieval task from one query to one target to multiple queries to multiple targets, accommodating the ambiguity inherent in long documents and images. As we can see here, the in the image or in the figure here, there are some ranking. So it will training into a ER classifier and it will go to the descending order. So it will rank the uh, this and it will classify to the classifying to will go to uh, ER classifier and go to descending order too. So the second stage is the summary-based ranking or SR. By summarizing long documents as queries and using entity-based image candidates from the pre-computed shared index, SR further mitigates ambiguity, making the framework robust against partial text-to-image associations and reducing encoding time. So here there are some keyword image index and it will uh, summarize the re-ranking the keyword and find the image. After it finds the uh, keyword and image, it will store and go to the query image and the visual image feature to find the image, and it will store and find the here as we can see is an apple, so it will go to this part and re-ranking the apple. So the main contribution, they want to introduce the two-stage course to find index shared retrieval or Cfir framework to tackle the effectiveness and efficiency challenges of state-of-the-art MLLMS based approaches in the more challenging real-world scenario with entity-based and summary-based ranking stages. We introduced a novel decoupling Bay tree encoder optimized for both ER and SR stages. This encoder employs a decoupled encoding designed for vector-based distance computation, enhancing both training and retrieval efficiency. Cfir is evaluated on the atomic dataset, showing an 11% improvement in recall 1000 and reducing computational times by 68.75% and 99.79% in training and retrieval, respectively. Related works: small-scale and caption-based text-to-image retrieval. A majority of existing text-to-image retrieval methods concentrate on small-scale and caption-based benchmarks, such as MS-COCO and Flickr 30K. It's often excelled by employing intramodal and intermodal attention mechanism to align entity semantics across modalities. For instances, for instance, MTFN introduced a generic text-to-image re-ranking scheme for refinement during the inference process without requiring additional training procedures. Moreover, JG-CAR and LibRR propose modeling the higher order neighbor relationship aware attention for text image retrieval in a learnable two-stage re-ranking paradigm. Recent advancement in multimodal large language models signify a paradigm shift in the field. In response, this paper proposed a novel two-stage course to find index shared retrieval framework tailored to address these challenges. And large-scale text-to-image retrieval datasets. Atomic is recently released dataset for large-scale long text-to-image retrieval introduced by Track 1. Atomic distinguishes itself by focusing on section-level image text association for multimedia content creation, emphasizing the use of English Wikipedia section without images for a more realistic text image context. Atomic is tailored for ad hoc retrieval tasks, reusing width image and metadata but providing image pixel values in standardized format. Therefore, Atomic is the only and best option to evaluate the performance of models in the context of large-scale long text-to-image retrieval. Evaluate long in this paper, we target the large-scale long text-to-image retrieval task in Atomic. This task is designed to retrieve images from large image collection based on long text query for scenarios such as article writing. Challenges in MLLM-based approaches. In regard to retrieval effectiveness, the issue manifests in two ways. First, the complexity and multifaceted nature of long document introduce semantic ambiguities. Second, this challenge is further exacerbated by the expanded pool of the candidate images. On the computational front, inefficiencies are also divided into two parts. First, the inference stage in current MLLM-based methods demands an exhaustive pairing of each query with database items. Second, the act of encoding long documents for semantic matching is itself a time-consuming process. So here in the methodology, the Bayes model is originally constructed as a multi-weight transformer design as depicted on the left side of figure 6. The multi-weight transformer block in Bayes 3 features shared self-attention models and a pool of feed-forward networks tailored for different modalities. To better fit the LLIR task, we propose a decoupling Bayes 3 as the MLLM encoder in our Cfir. Our debate tree architecture removed the vision language expert, as shown on the right side of the figure 6. This design is motivated by three primary considerations. First and most importantly, without the VL expert, we decouple the encoding of visual and text input and transition from model-based similarity inference to vector-based distance computation, which is significantly faster. Second, although Bayes design is effective for accurate instant-level alignment between text and images, it is optimized for image descriptions that are both precise and comprehensive. Third, our streamlined architecture result in 30.4 percent reduction in model parameters compared to the original Bay 3 model. For methodology, ER, the entity base ranking or ER stage served through two primary functions. First, it generates a top K ranking of images for each unique name entity extracted from long text queries, thereby mitigating ambiguity and partial associations. Second, ER effectively prunes irrelevant image candidate, paving the way for the subsequent re-ranking. To accomplish this, as shown in figure 3, we first employ the Advanced Natural Language Processing (NLP) library, SPACY, to extract name entities from each long document. SPACY robust entity extraction capabilities serve as an effective mechanism for generating entity queries. To achieve precise image matching, we introduced the summary-based re-ranking stage tailored for LLIR. Contrary to the ER stage, SR focuses exclusively on precise image matching of a document's key information document summary to refine the ranking of previously identified entity-based image candidates. BART supports a larger maximum input token count of 1024, accommodating the efforts token number of 419 in atomic queries compared to BERT token limit. The summary effectively mitigates during training. Only the language expert component of our debate tree is fine-tuned, leaving the remaining modules frozen. This approach facilitates the construction of pre-computed shared image embedding cage, striking an optimized balance between training efficiency and retrieval efficacy. The entire training process is optimized by a symmetric cross-entropy loss over the similarity scores between the text representation and image representation. Before do the experiment, there are some setup. We utilize the base H equals to 768 and large model or H equals to 1024 of our streamlined version of base 3 as our encoder in Cfir, denoted as Cfir B and Cfir L respectively, where H is the hidden size. Additionally, we include comparison with two state-of-the-art multimodal large language models, our proposed debate tree and OpenClip. So this section aims to evaluate the efficacy and efficiency of our proposed Cfir framework. Our evaluation encompasses both the base and large settings of the atomic datasets as discussed in section 2.2. So specifically, we answer the following research question. What is the benefit and cost of freezing the image encoder? How does Cfir perform compared to state-of-the-art approaches? How does the Cfir model demonstrate scalability in the context of the larger and more challenging atomic large setting? So as we can see, we evaluate the computational and performance traits of freezing the image encoder by comparing its performance with that of whole model fine-tuning. The comparison focuses on two models, OpenClip and debate tree, as detailed in upper block of table 1 for atomic base setting and table 2 for atomic large setting. The primary motivation for freezing the image encoder lies in the creation of an image embedding case, which substantially mitigates computational overhead on encoding image during both training and retrieval phases. For instance, the Bay3L version shows a decrease of 23 hours per epoch compared to the battery L full, while the battery B frozen exhibit an 8-hour reduction per epoch relative to the battery B full. This is particularly significant as model testing form an integral part of the training process. Such a duration is impractical in typical academic experimental environment. As for the more challenging scenario, atomic large setting which has 11 million long text and 11 million images, the battery L frozen demonstrate remarkable efficiency. As for another important aspect in evaluating the efficiency, the retrieval latency, the battery L frozen and the battery B frozen needs just 17.9% and 22.4% of the retrieval time required by the battery L full and the battery B full. This significant reduction in retrieval time underscores the enhanced scalability and aptness of these models for large-scale application. In summary, we construct and shared image embedding cache and shared entity-based image ranking index to markedly enhance training and retrieval efficiency prediction on the phrasing of the image encoder. This section investigates the improved performance facilitated by Cfir under atomic base setting by comparing it with OpenClip and the battery model, mainly in text-only fine-tuning setting because it is fair comparison to Cfir. For effectiveness, we observe that Cfir outperforms the previous states of the art model OpenClip frozen and our proposed the battery frozen under the atomic base across all metrics. Notably, Cfir is more effective with smaller encoder size. In terms of efficiency, compared to prior state-of-the-art MLLM-based methods, our approach incurs additional computational time and storage for constructing the entity-based image candidate index in the and the shared image embedding case. When compared to full model fine-tuning approaches, our Cfir still outperforms the previous stage of the art model OpenClip full. Cfir B gains 6.04% improvement on recall at 1000 compared to OpenClip B full. To summarize, under atomic base settings, Cfir outperforms state-of-the-art model OpenClip and the battery in both effectiveness and efficiency in text-only fine-tuning settings. For how does the Cfir model demonstrate scalability, the experimental results in the text-only fine-tuning setting, as detailed in the bottom block of Table 2, reveal that our proposed Cfir surpasses the battery frozen in atomic large setting across all evaluated metrics. In particular, Cfir B shows a notable increase of 0.006 and 1.91% in MRR at 10 and R at 1000 respectively when compared to debate 3B version. This result underscores severe better scalability as the candidate set size increases. In conclusion, within the challenging atomic large setting, Cfir demonstrates significantly improvement performance over the battery in terms efficiency in both text-only and whole model fine-tuning scenarios. So for the analysis, ablation study of Cfir using only the SR stage, we can see here in the table 3, leads to a significant improvement of 2.55% on R1000 and reduced training time from uh, 53 to 45 hours per epoch. This indicates that concise summaries enhance both retrieval and training efficiency by reducing document ambiguity. Comparative analysis in rows 1 and 4 in table 3 shows that integrating ER, a pre-computed shared index, and image embedding cache result in improved retrieval effectiveness. These integrations yields an improvement of 0.01 in MRR at 10 and 3.25% in R at 1000 and reduce the retrieval time from 400 to 1005.1 millisecond to 13 milliseconds per query. Specifically, it cuts down the training time from 63 to 45 hours per epoch and the retrieval time from 40 to 5 milliseconds to 40.7 millisecond per query, while achieving a 0.016 increase in MRR at 10 and 4.32% increase in R at 1000 compared to MLLM based approach. In summary, the ER and SR stages in Cfir contributes to both efficient image retrieval and improved performance metrics. Performance impact offering top K in entity-based ranking. The observation indicate that as the value of K increases, the re-ranking effectiveness of SR initially experiences a significant boost only to decrease slightly afterward. Specifically, there is an increase of 0.048 on MRR at 10 and 17.36% on R at 1000 when top K increases from 1000 to 10,000. Figure 7 showcases the practical outcomes of applying our Cfir framework within the atomic base ranking base setting. The figure presents a comprehensive view of the retrieval process, starting with the original long document, which consists of 398 tokens, and proceeding through the crucial stages of entity extraction and summarization. From the long text, 80 entities are extracted, 80 entities are extracted, highlighting the essential elements that facilitate the subsequent retrieval task. Furthermore, a brief summary of 56 tokens is generated, shorten the documents into a concise query. Additionally, it presents the rank image result yielded by both the ER and stages of our framework. As a result, as a result, Cfir not only enhances the retrieval accuracy but also speeds up the searching process, ensuring that the most contextually relevant images are brought to the forefront for final selection. So for the conclusion, in this paper, we address the challenges associated with large-scale long text to image retrieval. To this end, we introduced a novel two-stage course to find index shared retrieval Cfir framework designed to mitigate the ambiguity in long document while optimizing retrieval effectiveness and efficiency. The Cfir framework is modular, comprising two principal stages: entity-based ranking and summary-based ranking. These stages employ our proposed encoding module, decoupling by tree, which enable vector-based distance similarity inference and the use of pre-computed shared entity-based candidates index and image embedding case. This significantly improve training and retrieval efficiency. Our experimental results demonstrate that Cfir outperform existing state-of-the-art methods in the atomic LLIR task, as confirmed by both quantitative and qualitative evaluations. Thank you.